Everyone, so today I'm going to be going over my third crypto gauntlet. This is worth 60 points, and this is the hardest crypto challenge that I ended up putting in there. And so our prompt says, all right, I know 100,000% sure you won't get the flag unless you know your RSA. So I'm going to show you two ways to do this. I'm going to show you one, the way that you can just use a script online, and two, I'm going to show you the actual math behind RSA and how you can just do this with Python. So first, I'm going to just do a brief overview of Rsa encryption. Rsa is a crypto system up here. It's just a type of one-way encryption. So it utilizes prime numbers P and Q, and you multiply those together to get N, and then you have an E, which is public, and then you have your M, which is your original message, your ciphertext, which is C, and then you have your private key D. And I believe there might be more, but I will get to that later. And so I'm going to show you the two ways that you can actually do this challenge. But first, let me look over the rest of the hints. So the crypto library in Python has a few tools that can help you with this. I will showcase that after I show you the easy way. And how is Rsa encryption security impacted with a low N value? So what I'm going to show you is the easy way. So the easy way to do this challenge is I'm going to go ahead and copy our values here. So values.text to here. And then I'm just gonna, let's see what our values are. Okay, so it says decrypt my super epic RSA values. We have our C, our ciphertext. So this is the encrypted message. Our N, which is P times Q, and it's very small. N should never be this small because you can easily crack this into two prime numbers. And then E equals 2 raised to the 16th plus 1. So what the easiest way you can do this challenge is with a tool called Rsa Ctf Tool. So I'm going to go ahead and look that up, Rsa Ctf Tool. And we can just go ahead and get this off of GitHub, and I'll show you how you can just do this in one command. So with GitHub, you want to do git clone this, and then it will clone that repository, so we can go ahead and just go into it. And so we have our Rsa Ctf Tool.py. So let's go ahead and just run that file and see what we can pass it. We can pass it our N value, we can pass it the E value, and then we can uncipher, and then we can put in our ciphertext. So what I'm going to do is just, let's look at our values again, and then we can actually put these into this tool. So let's run Python 3 Rsa Ctf Tool.py, and then N equals, or tac N, I'm sorry. And then we can go ahead and put this value in. Then we can specify E, and then let's go ahead and compute this with Python. So let me just launch Python. It's 2 raised to the 16th plus 1. Okay, so this is our E value. And then we're gonna uncipher, and then we're gonna pass it the ciphertext. So there, and this will do all of the attacks for us, and it will give us our flag. So with this, you can just bypass all of the math that you have to do. This will just try every attack that it can think of. And yeah, so this is the flag. And now I'm gonna show you the actual math behind this and the way that you can solve this with Python. So I'm gonna make a file called, rsa.py. And then I'm gonna go ahead and edit this file. Just get a user bin environment Python 3. And then what I'm going to do first is just add in our variables. So here is C equals this, and then N is equal to this, and then E is equal, we know E is equal to 65537 because we ended up doing that earlier. Okay, sorry about that. I had to do something real quickly. Anyways, so we have our C, our N, and our E values. And now we can just go ahead and see how we're supposed to do the math of this. So you can go ahead and follow this key generation. So we compute N equals P times Q. So we have this N value, and how we can actually crack this is get our P and Q value. So we have to find we have to factor this into two prime numbers. And a great way you can do that is with FactorDB, factor database. And this will essentially go through its list of prime numbers and multiply them together and see if it matches this, much like how hashes are checked in a password. So we could see that it has actually cracked this into two very large P and Q values. So I'm going to open these in new tabs and just denote these values. I'm going to denote this value as P equals this, and then Q equals this other number. So factored database actually managed to find two proper values that it factors into. And now we can go ahead and look on to the next step. So we compute this event. I don't know what that is in Greek. I think it's a Greek value, but whatever. Toshin function. So the Toshin function is defined as Toshin equals P minus 1 times Q minus 1. I can't type. There we go. So we have our Toshin function. And now what we can actually do is, this is where the crypto library comes in, because we are going to have to do a modular multiplicative inverse. So we have to find our private key. So let me see if I can show you this. So you have to compute D, the modular multiplicative inverse of E mod n, or mod Toshin n, I'm sorry. So what we can do is actually use from crypto.util.number import inverse. And what this will do is give us a function, and we can just call, so we're going to compute D equals the modular multiplicative inverse of E mod Toshin. So we have our private value, and then now we can try to recover the original message. So I'm going to see if I can find where it shows how to do that. So we know that, oh no, this is just proof. Okay, never mind. This is just proof. I'm going to try to find where it shows how to compute the original message. This is, okay, so M raised to the E raised to the D. Okay, no, you know what? I'm just going to show you how I know how to do this. So we know that the original message is actually equal to C raised to the D mod n. And then if you wanted to find the ciphertext, if you were going to actually compute the ciphertext, you would do M raised to the E mod n. I couldn't find where it showed that on here, where it showed that you could like actually see it. But yeah, so this is what it is. So we don't need to compute the ciphertext in this case. We already have it. We don't want to compute the message. So let me just make sure we have all our parameters. We have our N, we have our D, our private encryption key, which is D, and then C, our ciphertext. So let me actually put this up here. That will not work if I put that there. And then upon getting this value, let's just go ahead and print M. Let's see what that looks like. So I'm going to run this. I'm going to run python3 rsa.py. And so we get our N value, or our M value, I'm very sorry. And so we want to convert this long to bytes, to an actual string. So what we can also use is we can use another utility from this. So from crypto util number, import long to bytes. So now we can actually print long to bytes of our original message, and this should actually give us our original message back. And there you go, it does. So this is our flag. So RSA is just a bunch of complicated math. There's different attacks on RSA. So like let's say if you have a very low encryption exponent, like let's say if this was 3, you could use some other attack. This attack is called the it's just like the very basic attack. Like n is very small, so you can just factor it into P and Q, and then from there you do all this, and then you get your value, or you get your message. But yeah, you can also use Rsa Ctf Tool. You can use that on a lot of CTFs that also have RSA problems. I highly recommend using it if you want to do CTFs. It's just this guy, Jana Patty, and then Rsa Ctf Tool. And you could just clone this. And yeah, let's go ahead and submit our flag. And there you go.